So good morning, everybody. This morning, maybe you are going to think I am like a UFO in this conference because my plasma discharge are fully different compared to the discharge that has been presented in this conference. The power is not in kilowatts, the energy is not in gigajoule, but the power is limited to about 1 watt in most cases, as we can see here. And I'm going to speak about atmospheric pressure discharge or near atmospheric pressure established in air. The usual application of such a discharge is mainly in chemistry for ozone production, for example, or for reduction of pollutants, or for surface treatment. But in our case, in my lab, we study the electrohydrodynamic phenomena occurring inside electrical discharge, atmospheric discharge. That is to say that we study discharge as an electromechanical converter that converts electrical energy into mechanical energy. It is a very prospective research. It's academic research. It is not applied. Maybe it will be in the future, but I don't know. So here's the outline of my presentation. I'm going to start briefly by an introduction. After, my presentation is divided into 2 main parts. The first one will be dedicated to volume DC corona discharge and an application on corona burst thruster. The second one will speak about surface discharge and an application to airflow control. So first, what is a ionic wind? You know, of course, that when there is a sufficient electric field at thin electrodes, there is ionization of the air. If we take an example of a needle with a grounded electrode in atmospheric air, and if there is a positive high voltage at the needle, then there is a positive ionization zone around the needle. And then the EHD force for electrohydrodynamic is the sum of each Coulomb force acting on each produced ion, each produced positive ion. And under this force, the ion drift towards the grounded electrode, as we can see here. They exchange momentum with the air molecules, and airflow is produced, which is called ionic wind or electric wind. So first, I'm going to speak about needle-to-plate corona discharge. So in this study, the goal was to investigate the transient phenomena occurring in a discharge produced between a point and a plate with DC high voltage, negative and positive DC high voltage. And for that, we developed a multi-methodology bench with ICCD, Stern visualization, and particle image velocimetry. I will speak about that because maybe you don't know what is it. So the experimental setup is very simple compared to your very complicated system. It's only a point and a plate with a gap of 25 millimeters between both, and we are going to apply a high voltage between both, and we are going to establish a discharge. The power consumption typically in these experiments is between 0.1 and 0.5 watts, so it's very weak. So, to visualize the produced flow in air, usually in fluid mechanics, we cannot see the motion of air with our eyes. So there is a very well-known method, which is PIV for particle image velocimetry. So in such a method, we had seeding particle, very small particle, typically with a diameter of 0.3 micrometer. And we eliminated this seeding particle with a laser sheet, and we take video with a camera. So in this case, we use a high-speed camera and a high-speed laser at 20 kilohertz, and we saw the flow in a plane. So here, oh, sorry. So here it is a point, here it is the plate, and we are going to see what's happened when we apply the high voltage. So just now, we apply the high voltage. We can see that the ionic wind jet starts from the point towards the plate and impacts the plate after about 10 milliseconds in these cases. It is a case of a negative corona. For a positive corona discharge, we can see we have still a unique wind jet starting from the needle, but it seems that the jet is thinner and speedier in the first millisecond. If we measure the time average velocity of this ionic wind, we can see a map here in the case of a negative corona discharge. So in background, it is the velocity in meter per second. We have here the point here and here, we have here the plate for increasing value of the negative high voltage. We can see that the unique wind velocity increases with the high voltage, and the maximum velocity is obtained around the needle where the EHD force takes place, because it is the region where the speed charge and the electric field are the highest. But if we measure the same thing with a positive high voltage, it is a positive corona in this case, with increasing value of the voltage, we can see that the topology is different. For voltage smaller than 20 kV, we can see that the maximum velocity is still around the needle. But from 40 kV in this case, and this gap is not always true, we can see that we have a constant velocity all along between the needle and the plate. That means that the HD force is not now limited to the ionization zone. And if we compare both, we can see here negative, here positive, we can see that the topology of the produced ionic wind is different. So now we are going to explain why. And if we plot velocity profile at midway between both electrodes, we can see this type of profile in the case of negative corona, here in the case of a positive corona. And what we can see is that for negative corona, the velocity is limited to about 5 meters per second. And with the positive discharge, it is limited to about 4 or 5 meters per second for voltage up to about 12 kV. But from 40 kV in this case, the maximum velocity, which is obtained in front of the needle, of course, suddenly increases. So the question is why? So now if we observe time resolve with unique wind, so I'm going to show you several instantaneous velocity field at different instants. So here it is at 1 millisecond, 2 milliseconds, 4 milliseconds, 8, 12. We can see, as I showed previously, that the jet starts from the needle here and propagates in quiescent air and impacts the wall, forming, when it impacts the wall, a three-dimensional circular vortex. Sometimes, as I explained you, to visualize the produced airflow, we have to add seeding particles, very small particles. In this technique, we assume that the particles follow well the flow. So that means that there is no slipping between the particle and the flow. But in the case of flow produced by a discharge, this particle can be charged and can be submitted to a phenomenon which is called electrostatic precipitation. So in order to confirm that the flow we observe with the PIV technique is relevant, we compared PIV with Schlieren visualization, which is a technique which does not require seeding particles. So we have here the view at 1 millisecond with the Schlieren techniques, and here with the PIV technique, and we can see that they are rather similar. So that shows that when using PIV, particles follow well the unique wind trajectory, when these particles are well chosen, of course. But there is another feature. If we observe this flow, we can see that the velocity is not constant along the distance between the needle and the plate. There are some unique wind gusts. So that means that the velocity is pulse. So to have the frequency signature of this pulse velocity, we can plot the FFT of the velocity at a given point, for example, and we have a peak at 3.3 kilohertz. So the question was why? Because it was the first time that somebody highlighted this phenomenon. And this phenomenon has been observed too by Schlieren visualization. So it is not due to the charge of particles. For example, here we can see the needle on the plate, and we can see this unique wind gust even with the Sharon technique, which does not require seeding particles. So to explain this phenomenon, we investigated the current versus time, and we conducted ICCD visualization. So here we have the current versus time for increasing value of the positive applied voltage. And here we have the corresponding ICCD visualization. And what we can see that for voltage smaller than 14 kV, so 14 kV is a very threshold in this experiment. The discharge current is only composed of a DC component, so that means we are in the case of a glow discharge. Physically, that means that we produce positive ions and they drift continuously towards the grounded electrode. But from 40 kilovolts, we can see that some current peaks, and these peaks correspond to streamer. So when you increase, it is well known as corona discharge. From a threshold, you pass from a glow discharge to a streamer discharge with streamers. And these streamers are confirmed by ICCD visualization. So we plot the FFT of the current, for example, as 16 kV here. And what we can see that we have still a peak at 3.3 kilohertz. So the unique frequency corresponds to the streamer frequency. So that means that at every current peak, so at every streamer, we have an acceleration of the unique wind due to the space charge of the streamer. What happened in presence of streamer? As we can see with PIV view, the velocity is pulsed at the same frequency, inducing a velocity increase, and this results in the increase of the time average velocity. So with streamer, it's a manner to increase the produced velocity. So now I'm going to speak very quickly about a few applications of this corona discharge. Lots of laboratories work on ionic wind for micropump application, for cooling application. For example, we can imagine that we have EHD pump in our laptop for cooling, for example. There is only one problem, is that produce ozone, so it's not so nice. And more recently, ionic wind starts to be taken into account in the biological and chemical plasma reactors, because the main application of this discharge is in chemistry and biology. But there is a new topic. It is a ionic wind bath thruster. So for example, we can imagine we have a wire to cylinder geometry. Here it is a cross-section view. So we apply the positive high voltage at the wire. So we have a HD force, a ionic wind, and then the thrust corresponds to the HD force, minus the drag, which is due to the ionic wind flowing around the cylinder. But this drag is very small compared to the HD force. So this idea is not so new, because here we have a video of the news of the day of 64 in USA. And it was very funny because it has been very hard to find this video. I have been lucky, I think. So it was during the news of the day, and they are showing the first prototype of atmospheric thruster. So it is a sort of engine with wire and grid, lots of very complicated. And to show it is the result of ionic wind, they use smoke below the engine, and we can see that the ionic wind moves the smoke towards the ground. But of course, in this case, the power high voltage, the power supply are not on board. It is a problem, of course. We are going to speak about that. So, a little history. The first scientific publication of this topic was the one of Christopher and Moreau in '67. And there have been a very important report by NACA in 2009, when they explained that we have to reach an effectiveness of about 20 Newton per kilowatt and a thrust density of 20 Newton per square meter to be maybe useful for atmospheric thrust. And the idea in the first paper was to use this kind of propulsion for low-speed, long-duration, small platform in near space, typically between 30 and 40 kilometers. So the idea was to convert, of course, solar energy with a solar panel into electrical energy to energize the discharge. But as I said, the effectiveness and the efficiency remains low. What's happened today? Today there is only about 20 papers on this topic, so it's fully new. In my own concern, I don't think that an aircraft will be propelled by this kind of propulsion in the future. But maybe it could be a propulsion system for small size UAV with onboard battery and solar panel. And this topic was sleeping. And last year, 1 year ago, a team of MIT succeeded in flying a 2.4 kilogram drone with a span height of 5 meters. We have the video here with this type of propulsion, and it has been published in Nature. And MIT has a very good service of communication, I think, because it has been presented on every news on TV. So now maybe there is a significant challenge to explore this new all-electric aircraft propulsion system. A few years ago, I published a paper. I developed a very simple model with 3 equations. This one is not mine because it is a Thomson equation. Here we have the thrust depending on the current. So we can see that the produced thrust is proportional to the current. It increases with the electrode gap, but it decreases with when the mobility of ions increases. And what about the effectiveness? We can see that the effectiveness is inversely proportional to the square root of the produced force. So it's not a good news. So here we have experimental measurements that confirm the theory. Here we have the current versus voltage. It can be well interpolated by this equation. Here we have the thrust as a function of the power consumption. We can see that the produced force depends only on the power consumption in a wire to cylinder geometry, of course. Here we have the thrust versus the current. We can see that it confirms this equation that the thrust is proportional to the current. And here we have the effectiveness versus the thrust, the produced thrust. And we can see, unfortunately, that that's right, the effectiveness really is inversely proportional to the square root of the produced force. So when you want to produce a high force, you reduce the effectiveness. So it's not good. Here is a curve for several gaps. We can see that the thrust increases with the gap. So a manner to increase the produced force is to increase the gap. But the gap is limited because when you increase the gap, you have to increase the applied high voltage, and you have a problem of insulating. And here we can see that the effectiveness increasing when you increase the gap. So, first conclusion about this first part. We saw that we can produce with DC volume discharge velocity up to about 10 meters per second, up to 12-13 meters per second. One value, the effectiveness is about 5 Newton per kilowatt per centimeter in gap. That means that, for example, for a small UAV with a gap of 10 centimeters, 1 watt can lift 5 grams, the order of magnitude. And we can imagine, because some laboratories start to work on unset robo, with very micro UAV, with very small gap, 1 watt can lift 0.5 grams. So, as a conclusion, it's not very easy to conclude about this topic because it's very new. To be simple, we can see that the type of propulsion, atmospheric propulsion, is comparable to small UAV propelled, driven by electrical motors. UAV we saw last evening in the sky. But the force density in Newton per square meter remains slow. And when we increase the thrust, we decrease the effectiveness. We increase the force density, but we decrease the effectiveness. So we have to find a compromise between all these parameters. But from 1 year, from the publication of the MIT team in Nature, now lots of laboratories start to work on this topic. So now I'm going to talk about another topic. It is airflow control that use always discharge, but surface discharge. So it is the context of airflow control. So the context is to use surface discharge established along a profile, for example, to manipulate the flowing along this profile. So there are, of course, an infinity of applications of such airflow control in industry, from very large-scale external flow in aerodynamics, for example, to micro-scale flow for microfluidic. There are lots of applications in fluid mechanics, noise reduction, thermal exchange, combustion. And today I'm going to speak on aerodynamic applications, which is flow detachment, flow separation. It is when the flow separates from the wall of the profile, because that results in losses, noise, and vibration. So to delay the flow separation, right now we can use passive system. For example, there are vortex generator we can see sometimes on plane, and that delays the flow separation along the wing. But more and more we want to be able to use active systems. We can be switched on or switched off as we want. So there are lots of solutions. There are suction, blowing, synthetic jet, the use of MEMS at the wall for vibration of the wall, for example, and plasma actuators. So what is this plasma actuators? It consists of generating a surface discharge at the wall within the boundary layer of the flow, and to use the EHD force on the resulting ionic wind to manipulate, to modify the near wall flow, very close to the wall. So the plasma actuators is usually composed of at least 2 electrodes, one air-exposed electrode and one electrode which is embedded. We apply the high voltage between both, and then a surface discharge is established, and that produces ionic wind. And we are going to use this ionic wind to manipulate the main flow. If we measure the velocity in this field of view, for example, we have this result. So we can see that we have a ionic wind jet which is parallel to the flow, and there is a suction effect above the discharge. These plasma actuators are very interesting because they are very simple and robust. There is no mechanic part, only 2 or 3 electrodes. They are low power consumption. We will see that they are quasi-linear converter, and it's very useful for real-time and closed-loop control. But the main drawback is that the produced velocity remains slow, typically about 10 meters per second. So here, we can see the first video we did in '99 with a plate. So we have an airflow coming from here. We have a plate, very simple experiment, okay? We establish a discharge between 2 electrodes here. Here it is without discharge. Now the discharge is switched on. So without discharge, now the plate is so inclined that the flow cannot be attached to the plate, so it detaches. And when we apply the discharge, we can see that we reattach the airflow. A more recent video, here we have a profile as a wing. It is inclined at 16 degrees, so at such a degree, the airflow detaches from the leading edge of the profile, and in aerodynamics that produce a decrease of lift. So if you are able to reattach a flow which is naturally detached, you can increase the lift. It's very interesting in aeronautics, of course. So we have a discharge here. Without discharge, it's separate. Can we see the vortex here? And with when we are going to apply the discharge, just now we can see that we are able to reattach the flow along the wall of the profile. So what about this actuator? The most known and unused actuator in this topic is a single DBD for dielectric barrier discharge. You know that it is composed of two electrodes, as we can see here. The dielectric between both electrodes is from a few micrometer to a few millimeter. And we apply usually a sine high voltage with a frequency typically of 1 kilohertz, but it can be 10 kilohertz as we want. The power consumption is usually smaller than 1 watt per centimeter in span-wise of the actuator. And here we have a view of a very simple actuator. It's just a glass plate with 2 aluminum foil stuck on the glass plate. And here we have a top view. So here it is the air-exposed electrode, and this one is encapsulated. We can see the discharge, and in the dark the discharge is like that. So first, what about this discharge versus time? So here we have time, and in black we have the applied voltage, and in blue we have the corresponding current. What we can see? We can see that during the positive going cycle, there is a streamer discharge because there are several high current peaks. High current peak for me, it's a few milliampere. Sorry, it's not ampere, okay? It's, yes, 50 milliampere. And if we have ICCD view, the edge of the electrode is here, okay? We can see that during the window A and B, we have a streamer discharge. So ICCD view confirm what we measure with the current. And during the negative going cycle, we have small current peaks, and we are in presence of a glow discharge. So the first information of this type of discharge is that we have two different discharges occurring during one IC cycle. A positive discharge, nothing here, and a negative discharge. So if we measure the thrust of this discharge, we can see that the thrust increases with the electrical power, and the effectiveness is smaller than a volume discharge, of course, because we want to produce velocity very close to the wall, where physics wants there is no velocity at the wall. So we induce lots of skin friction. So this decreases the effectiveness of such a discharge to produce a force. But the goal is not to produce a force. So if we measure the produced velocity in this field of view, as we saw previously, there is a jet with a thickness of a few millimeters, and the maximum velocity is obtained usually between 0.1 and 0.5 above the wall. And we know that if we are able to produce this maximum velocity closer to the wall, we will be more efficient. But if we observe the produced velocity versus time, we can see that it is strongly unsteady. For example, if we take 2 times in one period, so t 0.3 here during the positive going cycle, and here 0.55 during the negative going cycle, we can see that the produced sonic wind is fully different. During the positive discharge, the jet is thin and the velocity is weak. During the negative discharge, the jet is thicker compared to this one and the velocity is higher. So that shows that the negative glow discharge is more efficient in this case compared to the positive streamer discharge. It was the opposite for volumic discharge. And if we measure, for example, the produced velocity with another technique, laser Doppler velocimetry, at a fixed point, we have this sort of curve. So here we have in black voltage, time, and in blue here we have the velocity located at this point. What we can see? We can see that during the positive going cycle, there is a deceleration of the flow, and during the negative going cycle, we have an acceleration of the flow. That means that more times that the negative glow discharge is more efficient in velocity production, and that streamers does not contribute efficiently in this case to velocity production. And one very interesting thing is that a sine at voltage, at a frequency AC, for example, as you can see here, produce a rather sine electric wind at the same frequency with a fast shift depending on the position of this point. And that is true whatever the high voltage waveform. If you apply the square waveform, a sawtooth waveform, we can see that the velocity follows the high voltage waveform. So that means we have a quasi-linear relation between the high voltage waveform and the produced velocity. So it's very useful for flow control applications. So here it is a video of the produced uniqueen when we switch on the discharge. So here we have the surface of the plate. Here we have the air exposed electrodes. And we are waiting that this video starts again. So of course it is in quiescent air. So we start. And we can see that, as I said, the produced velocity is not constant. Okay? We can see velocity fluctuation at the frequency FAC of the high voltage. And we cannot see it on this video, of course, but we have an acceleration towards the wall during the negative voltage, and we have a deceleration during the positive one. Moreover, we can switch on and switch off the discharge, meaning that we can have both frequency, two frequencies in the produced uniqueen. And in fact, we can have the spectral signature we want in the uniqueen. Because, for example, in fluid mechanics, if you want to produce a uniqueen with the frequency in a given bandwidth, you have this bandwidth in frequency. You do an inverse E50 to have the signal that is going to energize the high voltage power supply. So you are going to apply the given waveform, and that will produce the uniqueen you wanted at the beginning. And what is very interesting for a few years with this topic is that we can imagine any geometry. Up to now, I show you only two electrode geometry. But the produced force is a spatial repartition can be modified with the electrode geometry. So for example here, we have 3D span-wise forcing with the sign topology of uniqueen. We wanted to produce a velocity as it is highlighted by the yellow arrows here. It was an application for skin friction drag reduction, and it worked well. Now we are working on a plasma grid. That means that the discharge are inside a hole, and it is for mixing enhancement. And we can have several actuators. In this case, it's very simple. We have only 8 independent energized actuators. And you can switch on, switch off each actuator when you want, where you want, and when you want. So here there's only 8 actuators, but in the past we can imagine we will have matrix of 100 or 200 actuators located on the first surface, and we can energize one actuator at a given time when you want. What's happened if instead of using a sine high voltage, we use a pulse high voltage with the same geometry? In this case, the HD force and the uniqueen are negligible because the pulse discharge are differently. In fact, if you use a pulse with a few nanoseconds in width, which is the case here, when you apply the pulse voltage, there is a thermalization of the gas at the wall, and that produces a pressure wave. You can see it here. So here we have the air exposed electrodes, and it is Schlieren visualization, where we can see the pressure wave at different instants, and this pressure wave propagates at a sound velocity. So one more time, instead of using the HD force, we can use the heat and the resulting pressure wave to manipulate an airflow. So it's not very important, so maybe I can continue. And one more time, if you modify the geometry of the electrodes, you can have the streamer propagation you want, and then you can modify the pressure wave you produce. So, just briefly a conclusion about these plasma actuators. With this, we can imagine we can bring energy either with a force or heat and a pressure wave, where and when we want. So now I'm going to finish with a few examples, very briefly, of airflow control. In fluid mechanics, usually, either we want to excite the flow to enhance mixing and spreading, for example, or we want to stabilize the flow to reduce a recirculation zone, for example, to delay a flow separation. For about 20 years, we tried, I think, about all the academic configuration we can test. I'm going to show you only 4 examples and only 2 slides per application, so it will be very brief. Cylinder, free jet, step, and airfoil. So here we have a cylinder. So maybe you can see why a cylinder, because it is an academic configuration. It's not applied and industrial application, I know, but there is lots of data of flow control on around cylinder. So we have, this is a course view, we have electrodes on this cylinder. And the goal in this study was to excite the flow by forcing the natural vortex shedding. Because we had very small amount of energy, usually the goal is to add energy where there are even already energy in the flow. So I'm going to show you only one example. It was at 55 meters per second. So here's a cylinder. The flow is here. So without discharge, we can see the flow is rather quiet. And when we are to switch on the discharge, there is a high flapping phenomenon down to the cylinder. So that means we increase mixing, for example. The second example is the flow at the exit of a round jet, as we can see here. Okay, so we are going to observe the flow at the exit here. It is the case here, with different frequency of the applied discharge. Here is the flow without discharge. And when we apply the discharge with different frequency, we can see that we have an increase, okay, of the width of the jet, meaning that there is a flapping mode in the jet, and the effectiveness depends one more time on the frequency. Here it is the maximum, it is the optimum frequency corresponding to a physical frequency of 40 Hertz, our Strand number to 0.1, and when we increase this velocity, the effect decreases. The third case is a very academic case. It is a backward-facing step, but it is a very interesting case because there are lots of phenomena occurring in these cases. So the step is here. There is an airflow coming here. So first you have a boundary layer. After you have here a flow separation due to the corner. After you have the vortex shedding here. And you have a recirculation zone, and the flow is going to reattach at this point, which is a reattachment length. And we have another recirculation zone here. So it's very funny to work with this type of flows. So I'm going to show you, we conducted lots of experiments with in this case, but I'm going to show you only two examples, one on the reattachment length, this point, and one about the shear layer dynamics, that is to say, the frequency, yeah, it's finished, the frequency of the vortex produced by the flow separation. So here we have the reattachment length versus frequency, and here it is the value of the reattachment length without discharge. We can see that we are able to reduce the recirculation length. And there is an optimal frequency, because in fluid mechanics there are always an optimal frequency. But the best feature is that the dynamic of the shear layer depends strongly on the actuation frequency. For example, here it is a case with actuation at 65 Hertz, and here it is actuation at 130 Hertz. And we can see that there is a lock-on phenomenon. That is to say that the shear layer frequency is driven by the discharge frequency. So we can fully manipulate the airflow. And to finish, two slides. It is experiment along airfoil. It was in a wide wind tunnel because we can see there are lots of students in this tunnel. It was with a 50 centimeter cord, and the Reynolds number was greater than 1 million. And one more time, we conducted lots of experiments, and just one result. Here we have the flow, the baseline flow around the airfoil at 13 degrees, and in such conditions, the natural flow separation occurs at 50% of the cord. And when we apply the discharge, we are able to delay this flow separation, and that is very interesting for aeronautic applications. So to finish, about these plasma actuators, we can say that they can work in a wide range of spatial scale, from a few micrometer to centimeter scale, on time scale. Maybe in a short term, we can think we will be able to act when on where we want, and we can bring energy either with a local force or heat. And it works in cruise condition, because of course we have tested all this feature in altitude chamber. But I think the most interesting thing is that in short term, it will be very nice to be able to build matrix of microactuator on the surface, and to be able to switch on and off each independent actuator when and where we want. What is the perspective? To be honest, the technology is not sufficiently mature now to be applied in industry. And to be really honest, I'm not sure we will see one day a plasma actuator on a plane wing. But it is a very versatile tool for in-lab experiments, because it is the only actuator which is able to bring energy where you want and when you want, very simply. And there are lots of other applications. And to finish, if we add volume discharge and surface discharge, maybe we can imagine a very small UAV propelled by volume discharge, the airflow flowing along this aircraft being controlled by surface discharge. Thank you for your attention.
Okay, we have time for a couple of questions. Eva?
Thank you for your fascinating talk. I have only one question, because you are in many of those applications you are making discharges in air. You have mentioned quietly and only in one moment production of ozone, yes. But this is also NOx, yes. Which are even worse. So how dangerous they are?
This discharge can be used to destroy NOx. So it depends on the type of discharge. To be honest, I don't know very well the chemistry occurring in this discharge, because it is very complicated between air is a soup, and you have lots of things in the air, depending on the environmental conditions, the humidity, and the chemical product depends on all these input parameters, so it's not so easy. But the main drawback of this discharge for application, for both applications I spoke today, is ozone production, of course. Yes.
Are there any other questions? Marek?
There were many, many numbers in your talk, many plots, and you started with saying that you will be talking about small numbers, 1 watt, etc. But also you were showing the range of, for instance, plasma electron densities, 10 to the 10, 10 to the 12. 10 to the 12, this is quite high density, actually. This is the ionization rate, I would say, is around 2% in such case, whereas, of course, with 10 to the 10 is much, much less. So what is the real, let's say, operation range? A real one. Because 2 orders of magnitude, well...
I cannot say you because I cannot measure it. to know that, we have to conduct numerical simulations. Of course, for example, in a point-to-plate configuration, the configuration is so asymmetric that this density depends on where you are in the electric gap. So it can be very strong where the electric field is strong, that is to say around the needle, and when you go towards the plate, it is lower, of course. But I think it will be too long to come back to the first slide with this, but the first one. Yes. I cannot give you a response because it depends on the, typically we are in this zone, below discharge, okay? So energy is this one, density is this one, typically. But it is a mean value. If you use a pulse discharge, for example, with a very small gap, you can increase this rate very highly during a very short time. So these values are mean value. And to give a range is very difficult because it depends on lots of input parameters, such as the waveform of the electrodes, the gap, and the waveform of the applied voltage.